So, just a word about the handout before I get started. So what I brought with me today for you guys is a handout that I produced for a gen ed course that I've taught in the past, Chem 100. Okay. So what's on here, and the reason I'm giving you guys this, because obviously this is a course for scientists, right? And we're going to go more into the depths of quantum numbers and exact electron configurations and Aufbau principles and Hund's rules and all of those things. Okay. But the reason I wanted to give you this document is to remind you of the big picture. Okay, so the material that's on here and the information that's on here is kind of the stuff. All right, for those of you who are coming in, there's a handout that's on the back desk there that you can get. The things that that you should just absolutely know and have in your head, this kind of understanding of the fact that electrons are responsible for chemical reactivity and how we know the important stuff about electron configuration. So the reason for this is, again, so hopefully you'll go back home, and when you're going over your notes, you'll read it. And this will help you keep in mind the forest so you don't get lost in the trees or the weeds, as people say. Okay, so I want you to remember kind of the big picture. Okay, so that's the reason I'm giving you this, and then we're going to be doing some practice in class on Friday about doing exact electron configurations and all of that, and learning the periodic trends that we observe. All right, so that being said, we're going to get back to the weeds for a couple minutes. So remember that quantum mechanics, okay, is essentially a mathematical model, a series of equations, okay, that acknowledges the wave-like properties of electrons, okay, and enables us to have some idea of how electrons are going to be arranged in space around the nucleus. Okay, so that's the big picture. Okay, so today we're going to start, okay, by talking a little more about orbital shapes and nodes and things like that, and then we're going to move into okay, I've got 20 electrons. Exactly which of those shapes is going to describe the behavior of which of those electrons, okay? All right, so we've got, to this point, we have built our model up, and we have a couple of different quantum numbers, okay? So n, okay, is going to be the quantum number that gives us the size of the energy level, the size of the orbital, the size of how far our electron is going to be if it finds itself in that shell, how far is it going to be from the nucleus, okay? Then our next kind of level of detail or honing down on where the electron is going to be is given by the L quantum number, okay? And that quantum number is going to give us the shape. And we have 4 basic shapes, okay, that when, combined at different energy levels get a little wackier and wackier, okay? But our 4 basic shapes, okay, are given letters to designate them. So we have S, which is just a sphere centered around the nucleus, okay? And so the S orbital, okay, at different n energy levels, okay, gets bigger and bigger. Okay, so that sphere gets bigger and bigger the greater your n value. Okay, so as we're traveling here, at the L equals 0 level, our sphere is a tiny sphere centered around the nucleus. That is when our n is 1. When we get up to a higher n level, a higher energy level, that s orbital has a bigger radius. Okay, so it's the electrons can go farther away from the nucleus. And then again, as we go up, it gets larger and larger. Okay, so what you'll notice when we look at the cross section, okay, of s orbitals at the n equals 3 level, what you see is that the sort of n equals 2 and n equals 1 are kind of nested within that n equals 3 s orbital. Okay. Okay. So and then at the end of class last time we talked about the p orbitals that have those 2 lobes. Okay. So some people call them dumbbells. Some people call them lobes. Okay. And what this means is that in this space around here, okay, you're not going to find an electron with that amount of energy. Okay, so you won't see electrons here, you won't see them here, but there's a possibility of seeing them anywhere in the space that's bounded by that shape. Okay. All right, so the next level of, or the next shape, or the next L level that we get to, we call D. Okay, and what the D orbitals look like, okay, is there are ones that look like these 4-leaf clovers. Okay, so we have those, and they're, again, the difference between these 4 different clover leaf shapes is just their orientation on the X, Y, and Z axes. Okay? So when you have, when you have 2 things like the p orbitals, just 2 lobes, okay, they line up in a line, and so you only have 3 possibilities: a line on the X, a line on the Y, or a line on the Z. Okay? When you add these other 2 lobes, okay, you get more orientations that you can have. So you've got, again, 4 different orientations for that 4-lobed shape. And then we have this other shape, okay, that kind of looks like a p orbital that's sitting in an inner tube. Okay? And so these are what the d orbitals look like. Okay? When you get to f orbitals, okay, we've got this infographic here that I had shown. Okay? When you get to f orbitals, you get much more complicated, weird shapes. Okay, so we're just going to talk about the basic shapes of the s, the p, and the d orbitals. Okay. All right, so that's enough about orbital shape, and that's what our second of the quantum number, okay, tells us. Okay. Now, when we talked about the p orbitals, we said they can be on the x, the y, or the z axis. They could be lined up in those ways. So we have a third quantum number, okay, that is used to identify that orbital. Okay. So if you look at these right here, so we have 3 possibilities for p orbitals in terms of shape and orientation. Okay. So the first quantum number n is going to tell us, the kind of base quanta that it falls into. That's the principal quantum number. The L is going to tell us that it's a p, that it's that shape. Okay? And the thing that's going to tell us whether it's the px, so this is our px, this is our py, and this is the pz. So the third quantum number, okay, which we call the magnetic quantum number, okay, is going to be related to an orbital's orientation in space. Okay? And the rules for that, okay, as to what that number is, are going to range from minus L to plus L. Okay? So, if you remember, okay, L can go from 0 to n minus 1. So let's say our n is 2. Okay? Then our L can be 0 or 1, and we did that last class, and you can see it written in pink up above. So what our M sub L, that's our magnetic quantum number, can be, okay, means that we can go from minus L to plus L. Okay, so if L is 0, okay, there's no minus plus 0, so it will be 0. Okay, and then minus L to plus L, well, if L is 1, it can be minus 1 or it can be plus 1. So at the n equals 2 level, how many magnetic quantum number values can I have? So how many numbers did I write there? 3, right? And we looked at the p, so this is, again, this is p orbitals. And when we looked at the p orbitals, we've got a px, a py, and a pz, right? So these 3 numbers right here, okay, correspond to our px, py, and pz, okay? So our shapes that we get, okay, if we look, if L is equal to 1, we have a P shape. So that's P, okay? And if L is equal to 0, we have an S shape, okay? So, all right, I made a slight mistake with the magnetic quantum numbers. So this 0 right here, okay, is when we go from minus L to plus L, if L is 1, minus 1, 0, plus 1, if you're going on a number line. So that's where that 0 comes from, okay? So these magnetic quantum numbers refer to those p orbitals, okay? When L is 0, you have s orbitals, okay? That's the s orbital shape, okay? All right, so when n is equal to 2, okay, what this tells us is that when we have the second shell amount of energy, we have electrons in both s and p orbitals. If n is equal to 1, okay, so let's say n is equal to 1, okay, our values for what L can be, they can go from 0 to n minus 1. Well, if n is 1, 1 minus 1 is 0, right? So L can only be 0, okay? And then again, our M sub L, okay, it can go from minus L to plus L. Well, it's just going to be 0, okay? So what this tells us, okay, is that when n is equal to 1, when we're at that first energy level, we only have s-shaped orbitals, okay? So only s orbitals at that lowest energy level. As we get more electrons in our system, as they have more energy, okay, we're going to have higher n levels, okay, and we're going to have more orbitals. All right, so when we get to n equals 3, okay, these L values and M sub L values, we're going to get more of those. Okay, so up to this point, okay, this is just a chart that shows you if we went through, doing all these numbers for all values of n, okay? Up to 4, okay? All right, so again, to give you kind of a preview where we're going and to get into keeping us in mind of the periodic table and how it helps us, okay? Those row numbers, okay? Those row numbers tell you what n is for that element, okay? So for its outermost electrons. So I can look, and without having to go through, and we're going to learn how to place all the electrons in orbitals, okay? But I can go right now and I can look at cesium. Okay, it's in the first group. It's in row 6. Okay, and so I can tell you immediately, okay, that it's going to have, that its n value for its outermost electrons is 6. Okay, and the orbital, again, the orbitals that are going to be filled are going to be filled all the way up until 6. Okay, it's in group 1. Okay, that tells me that its outermost 6th level of energy has 1 electron in it. Okay, so I can go over to the halogens to it's group number 17 here. But remember in our AB notation that you have on your periodic table, that's group 7A. Okay, so I could tell you that chlorine, okay, because it's in row 3 and group 7, it has 7 electrons in its outermost highest energy level, and they are in energy level with quantum number n of 3. So again, that's where we're going. This is how the periodic tables are a cheat sheet. Okay? So we're going to go into the details, okay, and then we're going to zoom back out and say, okay, here's how you use the periodic table to not have to do all this detail stuff. Okay? If I want to know, if lithium's going to react with fluorine, okay, I know one has 7 electrons at its outermost level, one has 1, okay, and we're going to talk about the octet rule, about how electrons are always trying to get that outer level filled. And so the easiest thing to do is for lithium to give up 1 electron and fluorine to take it. So now fluorine has 8, and 8 is the magic number that those noble gases have. Okay? So I'm going to be able to predict, just based on where something is in the periodic table, how it's going to react. Okay? And so as we go through, again, all these wacky quantum numbers, don't forget, okay, that they reflect the organization of things on the periodic table. And the reason the periodic table was organized the way it is because people did experiments and they saw how these things behave. And then when it come to the early 20th century, we had an explanation for why they behave that way. And that's the quantum model. Okay? So we're going into the explanation for why, okay, and then we're going to zoom out and we're going to focus on the what. Okay? All right. Boy, I felt like I was preaching there for a minute. All right. Preaching the gospel of chemistry. All right. So let's just talk about, again, where the electrons ain't and what we call those places in space. Okay? All right. So when we have these electron spaces, shapes, or these orbital shapes, okay, again, they represent the regions of space where the electrons are going to be, okay, and the size of them, right, how big they are, represents, again, where they can be, how far away from the nucleus, but also, the bigger the shape you see, the more energy that electron has, okay? And then the places where there is no shape, okay, are space, regions of space where the electron is not going to be. And we can draw planes, okay, through those spaces, regions of space, and we call those nodes, okay? So again, if you have a node in a function, a mathematical function, it's a place where it kind of goes to 0, right? And so these are these planes that you can draw that kind of bisect some of these orbital shapes are places where you're not going to see an electron. The probability of the electron being there is 0. Okay? The probability of me being in my office between 9 and 9:50 a.m., Monday, Wednesday through Friday, is 0 because I'm likely to be in this room because I teach in this room, right? All right. So probability of electron being located in these regions is 0. Okay? And again, that reflects the math. That reflects that when you plug the numbers into those wacky, equations that we use to describe quantum mechanics, they're going to go to 0 at those points in space. Okay, so those are what planar nodes are. Okay. Now we also have, regions of space that are what we call spherical, okay, ball-shaped, where electrons aren't going to be. Okay, so spherical nodes are things like you see here. I'm going to use a color that shows up better. It's one of the things I love about my tablet is I can use pretty colors. All right, so if we look, okay, the space that I've shown in pink here, okay, is kind of empty in the cross section. Okay, that's what we call a spherical node. Okay, it's a round shape. Okay, and that space is going to be empty. There are going to be no electrons there. Okay, so that's what we call a spherical node, and we have them, and they're seen, in all the different orbital shapes. Okay. All right. So, yes.
Wasn't that just in one of the other S orbitals?
Oops.
You said that you can see the
So
2s.
so you can see. So here's 1s. Okay. So I'm going to color the 1s yellow, right? And then in between the 1s and the 2s,
There's another.
okay, there's going to be a spherical node.
Okay.
Okay. And in between the 2s and the 3s, there's going to be a spherical node,
Which is that pink space.
which is the pink space. Yep. So, good question. All right. Okay, so we're going to take a minute, talk about the difference between the hydrogen atom and everybody else. Okay, so when you have the hydrogen atom, it's only got one proton in the nucleus. It's only got one electron. Okay, so hydrogen, its orbital energies wind up only depending on the main shell. Okay, so this is a single electron system. And a single electron system is really the only one that we can do the math for with our quantum model on pencil and paper. It's not fun to do it on pencil and paper. As someone who took quantum mechanics in graduate school, I can tell you that doing the math on paper is not fun, right? But we can come up with sort of simplified equations that will describe the behavior of electrons in a hydrogen atom when you pump more energy into that hydrogen atom, okay? So, normally the electrons are going to want to be here, right, in what we call the ground state. But if we add energy to that hydrogen, like we have hydrogen gas in a tube, and we run an electrical current through it, okay, those hydrogen electrons are going to absorb energy, and they'll jump up, okay, to higher energy levels, okay, and when they jump up to those higher energy levels, they're still going to follow the rules for the orbital shapes of where they can be, okay? All right, so we can calculate those based only on their n number, where they're going to be. So what you'll see, again, is everything that's n equals 2 kind of has the same amount of energy. Everything that's n equals 3 has the same amount of energy, no matter the orbital shape, okay? That's a nice, simple system, okay? But we've got, 90-something other elements that have more than one electron, okay? And things get more complicated, okay? Because, okay, remember, even just remembering the simplest force that's going to be at play here, like just the fact that charges interact with one another. So the more electrons you have, the more negatively charged things you have outside your nucleus, and those charges are going to repel one another, right? And so if I have 2 electrons in my system, okay, that one electron is going to repel the other, okay, and and their behavior is going to affect each other, okay? Now add a third one in, and now you've got, it's like a love triangle. You've got, although it's a hate triangle, right? They repel each other. And so now, okay, I've got to account for the influence of, this one on the other two and this one on the other two. When we add 4, now we have more interactions. So the more electrons you have, the harder it is to account for all the things that might affect their behavior, okay? And the larger the amount of differences, okay, in energies between individual electrons can be, okay? So for all other elements, okay, the energy associated with electrons in a particular orbital, okay, is going to depend on not just their energy level, okay, not just the N number, it's going to depend on their angular momentum and their magnetic quantum number, okay, so those other two quantum numbers. So bottom line for this is why we get these diagrams that will show you that a 1s orbital is lower in energy than a 2s orbital, but even though the p orbitals at the n equals 2 level are at the same kind of base quanta, the p orbitals are a little bit higher in energy than the s orbitals. Okay, so we have basically a hierarchy of orbital energies, okay? As long as you're at the same N number and the same L number, okay, then you're going to be, you're going to have the same energy, okay, in terms of, so all the 3p orbitals are energetically kind of equivalent. All the 4d orbitals energetically equivalent, okay? All right, so that gets us, again, through chapter 3. So now, okay, we're going to drill down one more level, okay, and talk about individual electrons and who's in the 1s orbital, who's in the 3p orbital, how do you get there, how do you decide who goes where when, okay? All right. So, here's chapter 4. Ta-da, we finally got here. All right, so this is, again, what we call electron configurations. We're not going to, again, we're going to go through the basic principles of, the microscopic electron configurations and teach you, again, how to organize electrons. And then we're going to rapidly zoom out and focus on, okay, how does this affect their reactivity? Okay. All right. So we've got all these lovely new words and terms we're going to use. And so these are the things, again, you'll notice that we are adding a new quantum number. The fourth one, I promise it's the last. Okay. And how these, again, how those quantum numbers are going to dictate where your electron is. Okay. All right, so this is, again, these are the quantum numbers and the number of orbitals, okay? And that's what those first 3 quantum numbers tell us. The fourth quantum number is going to tell us, okay, it's going to tell us exactly where the electron is, okay? All right. So, what is that fourth quantum number? Okay, we call it the spin quantum number. Okay, so the spin quantum number, we use the symbol m sub s for. Oops, it's a little s. So we got the magnetic quantum number and then the spin quantum number. And ironically, the spin quantum number is responsible for materials being magnetic or not, okay? So the magnetic quantum number does not have to do with magnetism, okay? So what do we mean when we talk about electron spin? Okay? Well, it turns out that, electrons are not just flying around, they're spinning on their axis like the Earth is. Okay? So, okay, they're waves, but they also have this particle nature, and the particle itself acts like a little sphere that's spinning around. Okay? But remember that it's charged. Okay? So when you move a charge, you create a magnetic field. Okay? This is how we get our electricity from things like hydroelectric or wind power. Okay? You have something mechanical like the force of water. Okay? That is moving. Okay? A magnet with respect to a coil of wire. Okay? And that induces charges to move in the coil of wire, and you get interactions between the magnet and the electric field, and eventually you can turn your lights on. Okay, so we've got moving electrons, moving charges create our magnetic field. Okay, but when we talk about spinning, okay, an electron spinning, just like the Earth spins on an axis. And our electrons spin on an axis. But unlike the Earth, which spins in only one direction, okay, you can have an electron spinning clockwise, or it can spin counterclockwise. Okay? And so what we call these are up and down spins, okay, because a moving charge, okay, creates a magnetic field. Magnetic fields, magnets have two poles, like we call them a north and a south pole. So if you have two magnets, two bar magnets, and you bring them towards one another, they're going to push each other apart. If the north poles are facing one another, they're going to stick together if the south poles or the north and the south pole are facing one another. All right, so this electron shown on the slide has an up spin, okay, and this one has a down. Okay, so we've got two possible spin states. Okay, so these are our two possible spin states. Okay, so the spinning happens, going to the left or counterclockwise, or clockwise going to the right. That produces a magnetic field that's either up or down. And so we call the spin state of the electron either up or down. And we use little arrows to refer to it as the up or down spin. So that's our final quantum number. So when we go back to, all of these individual orbitals, okay, we're going to find that an individual orbital, one of those little boxes that was on one of the previous slides, okay, can have up to 2 electrons in it. Okay, so the region of space that's, that 1s sphere, okay, there can be 2 electrons in that region of space, but one of them is going to have an up spin, the other is going to have a down. Okay, and then when we get to the p orbitals, okay, your px orbital can have up to 2 electrons, but one has to have an up and the other has to have a down spin. Okay. All right. So, just talking about, since we're on magnets, okay, what makes something a magnet or not a magnet, okay? So, magnetic properties of materials, okay, this is of materials, come from the additive effect of electron spins on a microscopic level, okay? So, we've got 3 materials shown here, and the circles represent the atoms in that material, okay? And the way those spins kind of line up in the material, okay, gives you kind of the properties of that material with respect to how they behave in magnets, okay? So, things that are what we call diamagnetic, okay? So these are things that you would not consider magnets, okay? So, not magnetic materials. So things like the wood that this podium is made out of. I can put a magnet on it and it will slide right off. It won't stick to it because the atoms in this wood are diamagnetic, okay? Electrons are paired and they're not attracted, they're not magnetically attracted to anything. So the other two types of materials are what we would consider permanent magnets and materials where you can induce a magnetic field in them, okay? So paramagnetic materials, okay, have one or more electrons that are not paired, okay? So remember in an orbital, you can have electrons be paired up or not, okay? And so in diamagnetic materials, all the orbitals have paired electrons. In paramagnetic materials, you may have your outermost orbital, your highest energy orbital, may have only one electron in it, okay? And those materials, okay, the magnetic fields may be pointing on all different directions in your in that material. Okay, and this is like a common state. Lots of paramagnetic materials. Okay. So one or more unpaired electrons, and then what we call the magnetic moments. So these little arrows that are shown on the slide in the circles. Okay, those are magnetic moments, which means if you're thinking of the north and the south pole of a magnet, okay, of a bar magnet, then the arrow's pointing to the North Pole, the beginning of the arrow is the South Pole, okay? So that arrow shows you the direction of the magnet, and if, things are, so if I have, let's say, right here, this end here would be the South Pole, this end here would be the North Pole of the magnetic field in that particular atom. And so these things would kind of be attracted to each other, okay? All right, but the material overall doesn't have things lined up. They're pointing in all directions, so they kind of cancel each other out. Okay? Now, in ferromagnetic materials, okay, these are what we consider real magnets. So I take, a magnet on my refrigerator, or the stylus for my tablet. It sticks to the side of the tablet, okay, because I've got a magnetic material, and it's going to stick to the iron that's in the outer case of the tablet. Okay, so in that case, okay, I have this case where I have at least one unpaired electron, but the magnetic moments, the poles of those magnets from our spinning electrons, okay, all point in the same direction. So what that means, okay, is all of them have the south pointing in the south direction, okay, and all of them have the north pointing in the same direction. They all line up. So when this material meets another magnetic material, okay, they are going to line up and stick to one another, okay, so that the South Pole and the North Pole are attracted to one another, and so that's how you get what's called a ferromagnet. Okay. Now, paramagnetic materials, okay, they can be induced to become magnetic, right? Because I've got the unpaired electrons, okay? So if I subject them to like a strong magnet or an electric field maybe, I can get those to line up, okay? So these can be induced to create, a magnet, okay? So that you would have all the things line up, okay? So things that we consider electromagnets, materials that are not magnetic, but when you run an electric current through them, it causes the spins to line up and create a magnetic field, okay? Those are paramagnetic materials. So if you've had an MRI, okay, the way that we get an image, okay, out of that instrument, okay, is we utilize the properties, the magnetic properties of our electron spins, okay? So what we do is we run an electric current through a material to create, that is paramagnetic, to create a very strong magnetic field, okay? That's going to affect the spins in the nuclei of some of the atoms in your knee or whatever when you're getting your MRI, okay? And then we do things to kind of disrupt that. Okay, we send radio signals, and then we look at, when we remove the disruption, like how things respond. So we're really playing around with the spins of the nuclei when we do things like take MRI scans of, body parts. Okay, and but in order to create those fields, we need special materials. Okay, so the materials in those devices are what we call superconductors. But in order to be superconductive and create these very strong magnetic fields that we need, because you need a strong magnet to be able to go through tissue and affect the spins in your electrons in your in your atoms, let's say. Then what happens is those materials have to be cooled down to very low temperatures to be able to get the current to be high enough to create the magnetic field. Okay, so in addition to your the electrons, okay, having spin, okay, the protons in your nucleus also have a spin. Okay, so we're using the properties of the electrons to create the field, and we're looking at the nuclear spins, how they respond to that field. Okay. All right, enough about magnets. So we're going to talk about two principles, Pauli exclusion and Aufbau. These are rules, okay, for how electrons go in orbitals. Okay. So the Pauli exclusion principle is the no identical twin principle. Okay, so Pauli exclusion is really no identical twin electrons. What does that mean? It means nobody can have the same 4 quantum numbers. Okay, so what that means is I can have my first 3 quantum numbers can be the same. Okay, my 4th quantum number can only have 2 possible values, the up and the down value, right? And the number we give to those are plus 1/2 or minus 1/2. So again, you can think of them as the up and the down. And the 1/2, just think of as an orbital, an individual orbital can have 2 electrons in it. And so the plus 1/2 is 1 out of 2 is up, and the minus 1/2 is 1 out of 2 is down. Okay? All right, so the Pauli exclusion principle is that an orbital can only have 2 electrons. Okay? The first 3 quantum numbers are going to be the same, but the 4th one has to be different. Okay? And they're going to have opposite spins. Okay? All right. So again, if we have 1 electron, okay, we don't have to worry about, about the partner. If we have 2, okay, we are going to pair up electrons with opposite spins. Once we get a 3rd electron, okay, then we go to the next orbital. Okay, so as we add electrons, okay, we fill lower energy levels with paired electrons before moving to the next energy level, okay? Now notice that I did not say we paired orbitals up before going to the next orbital, okay? So just remember energy levels, okay? Because we're going to be individually placing orbitals in, let's say if we're doing p orbitals and there's 3 of them, we're going to place an up spin electron in each one of those before we start pairing them up, okay? All right, so, oh, we still have time, good, okay. So we showed this at the end of chapter 3, right? Single electron atom, our energy is only going to depend on distance from the nucleus. So remember, as we go up in energy, we go farther from the nucleus. Okay. And in multi-electron systems, okay, we've got more intermediate steps, okay, between the orbital energies. All right. So again, I said in multiple electron systems, we have to consider that electron-electron repulsion, okay, and the impact that those like charges are going to have on one another. And so that electron-electron repulsion is going to be different based on the shape of the orbital. Because if we think about it, okay, if I have an s orbital, okay, and I have an electron here, and I have an electron here, okay, I'm in a circle, and they're either going to be, closer or farther apart from each other. Their, distance is kind of bounded by the outer bound of the sphere. Okay, if I have a slightly more complicated shape, okay, and I have like a p orbital, okay, oops, that was not good. You know what I'm going to do? I'm going to cheat and I'm going to copy and paste the same shape, okay? Okay. But now I'm going to move this electron so that it's over here, okay? All right. The constraints on where the electrons can be are different, okay? So the forces that are between those electrons, okay, are going to be different when I have a sphere versus when I have this bilobe shape that has a planar node through it where no electrons can be, okay? These electrons in this sphere can be anywhere in that sphere, okay? But if I look at this electron here, or this electron here, and this electron here, they're going to repel one another. If this electron decides, to go this way, okay, it's going to enter a region of probability where there's no probability it's going to be. So it's going to have to go somewhere else. So the rules about where it can go are more complicated. Okay. All right. Okay, so we're going to start on Friday with talking about, again, what do we do when we have more than one electron? How do we decide who goes where? Okay, and then what does that mean, okay, in terms of things like chemical reactivity? So in lab this week, you're making lots of observations on, as I go down the group of alkali metals, how does the material behave differently, okay? So on Friday's class, we're going to start to get into the explanation of, why lithium and sodium don't give you the exact same reaction. They react with the same partner. They'll react with water, okay? But the nature of that reaction is a little bit different, okay? So a reminder, I sent a message about lab this week. There's a whole portion of the lab that requires you to write reaction equations. we haven't, we're covering that later in the semester, and we just forgot to take that part of the table out of the lab manual, so we'll give you those in lab. So, yeah.
No, I was gonna say,